This person is from Ireland, Society for Science and the Republic, from Skerries Community College. We're talking about Adam Kelly. Give him a warm applause. Welcome, Adam.
Hello, my name is Adam Kelly, and I'm from Dublin in Ireland. And I'm really excited to be talking to you guys about my research into quantum computing. And don't worry, there's not going to be any experiments, or we're done with that. So I've always been interested in computers. I taught myself how to program when I was 10, and since then I've kept up with what's been going on with technology. When I first heard about quantum computing, I thought it was a really interesting topic, and I wanted to know more. I bought some books, I started reading articles and research papers, and I got really, really excited as to what the possibilities were. I started playing around with the concepts that I was learning, and eventually wrote some simple software which seemed to do quite well. So I started looking to see what I could do to maybe do some contribution to the field. So before I continue, I'd like to talk a little bit about what quantum computing actually is. So if you think about a computer like you might have at home or in your phone, for example, it works using bits, zeros and ones. With these bits, you can store information, represent information, and then do whatever computations you need to. And this works very well for certain types of tasks, and we've got computers, so they work. But quantum computers are different. Quantum computers use the principles of quantum mechanics to perform computation. Instead of using zeros and ones, we use what is called a qubit, a quantum bit. And what's special about these is that they're not just 0 or 1, but they're actually a combination of both at the same time. Kind of. So what you can do with these qubits is you can then interact with them. So you can use multiple qubits at the same time to then go and solve hard problems. And the type of problems that they solve are ones that are really important and are ones that, most crucially, we can't solve already. So my research looks at what's called quantum circuits. So if you're going to go and write some code at home to try and run a program, it's quite easy. You just, tell the computer what you want to do. A quantum circuit is the same thing. It's just a diagram like this, and each part of the diagram represents something that the quantum computer has to do. My research is looking into how we can simulate these quantum circuits in the most efficient way. So to do simulation, you want to take in some sort of input, kind of like a programming language. Then you do whatever simulation you need to perform, and then you just return the output, similar to how you would have performed the operations on an actual quantum computer. So this seems rather straightforward, but I set out to do my research and to write some software that was, first of all, usable, so that anybody would be able to go and simulate whatever circuits they needed to, and most importantly was high performance, so it was faster than any other simulator on the market. So why is this hard? See, it's very easy to write a very simple simulator. You just take the maths and you just put it in a programming language and you're done. But the problem is that gets very, very slow, very quickly. When you have a quantum bit, there's only two states, a 0 or a 1. But then once you have two, you have to keep track of a 0 and another 0 and a 0, 1 and 1, 0 and 1, 1. That's 4. And every time you add another quantum bit, you have to double the amount of information you're storing. So even when it's a very small simulation, it gets very slow very quickly, and it uses a lot of memory very quickly. So the way I solved this problem was doing something which is quite common in physics and in maths, which is looking for structure and symmetry within the problem. On screen is three quantum circuits, and each of them looks somewhat random, but in fact, each of them contains specific structures that can be used to improve the way that they're being simulated. So what I wanted to do was to try and recognize this type of symmetry. So, for example, one type of symmetry would be in the operations that you're actually performing with a quantum computer. The operations can have specific mathematical properties that make them well suited to specific types of simulation and can be very, very fast. Alternatively, because quantum computers are actual real devices, they've got physical limitations. So for example, on screen, there is a quantum computer from Google. And what's special about this is that the quantum bits are laid out in a grid, and only the bits that are right next to each other in the grid can interact with each other. So what I want to do is I take a new preprocessor, you take in whatever circuit you want to simulate, and you try and look for these types of properties. From there, you can then go and select a simulation method which works well for that given case. To make it even faster again, I wanted to use high-performance computing techniques. These are things like using graphics cards and supercomputers, just like you would if you were, for example, running a video game. To the left is a photo of a supercomputer. This is one that I actually got to use during my project, which was very exciting, but also quite difficult to use and to learn how to use. And in fact, I was able to actually get all the things working together, so multi-threaded, GPU, supercomputer stuff. So it was quite interesting. And what this meant is that all of these factors coming together means that you can get a massive speed increase against other simulators. I was able to get about 120 times faster, and I was able to simulate up to about 37 qubits using big nodes of the supercomputer. And what this means is that you're then able to go and develop and test quantum algorithms easier than before, which is important because we don't actually currently have big quantum computers. And also, quantum computers contain certain amounts of sort of hidden information which you can't get on any other way apart from simulation. So this means it's easier to develop algorithms for things like doing chemistry. So for example, on screen is a picture of lithium hydride. And what we can do is we can actually go and we can perform experiments using a quantum computer, and we can actually simulate how it would handle these tasks. Doing research has brought me all over the world. I'm still in high school, but I've still been able to go to about 4 different science competitions. I was invited to the NSA. I've been here in Sweden. I'm going to London. I've been to Bulgaria. It's been absolutely amazing. So if any of you have ever considered or want to go and do research, I would encourage you to go and do that because you never know where it's going to take you. Thank you.
Wow, thank you so much. High five, Adam. Good work. Can we give one more applause to Adam Kelly here? Fantastic. How did it feel to talk about your passion and your work now for this audience here?
Fine, yeah.
Yeah, it was good. What makes you most excited and most happy, like in the work you do? Like, what drives you, or what drives you to go forward with it?
Well, the reason I got started with this all in the first place was not because I had to do it for school or anything else. I just, like maths and I like computers, and this was just a good way to play around with both under what I wanted to do and explore the things that I was interested in. So whenever I was working on it, it was solving interesting problems that I wanted to be working on. So, there's no real better reason than that to do it.
That's amazing. Thank you for sharing your interest. I will take back this click over here, and we will give back the biggest applause to Adam Kelly. Thank you so much. Yes.